So today I want to talk about the golden ratio. And there's a lot to say about the golden ratio, and I can't say it all in a short video. What I'll try to do is give a sense of conceptually how you might define the golden ratio, a couple of cool properties that it has, and then actually derive a sort of algebraic expression for this number. So first, the idea. What is the golden ratio? Well, it starts with a line. And we think about dividing this line into two pieces. And I'll label the lengths of these two pieces x and y. And the idea of the golden ratio is to divide this line in such a way so that the ratio of the longer piece to the shorter piece, y divided by x, is exactly equal to the ratio of the whole line, x plus y, to the longer piece, y. So this equation is what defines the golden ratio. The golden ratio is often called phi, so the ratio itself is y divided by x, or equivalently x plus y divided by y. It's the ratio of this length to this length. But we can use this equation, manipulate it, to figure out what phi is. So one thing we can do from here is multiply both sides by y and by x. That gives us y squared equals x squared plus xy. Rewrite this as y squared minus xy minus x squared equals 0. Now at this stage we have an equation, but it still has these two component pieces, x and y, the two lengths of the line once we split it up. What I really want is phi, which is y divided by x. So to get phi, I can divide both sides of this equation by y squared. So that gives me y squared, by x squared. So that gives me y squared divided by x squared minus xy divided by x squared minus x squared divided by x squared equals 0. Now this is just y over x squared, so that's phi squared. The x here cancels and we get y over x, which is phi, and this is 1. So this quadratic equation is the equation that defines the golden ratio phi, right, manipulated from up here. So phi is the value that satisfies this equation, the positive value. Now already before we solve this equation, we can use it to notice two kind of interesting properties of the golden ratio. One is just by moving this to the other side, we get phi squared equals phi plus 1. So adding 1 to phi is the same as squaring it. On the other side, or on the other hand, if I take this and I divide both sides by phi, then I get phi equals 1 plus 1 over phi. So from that I get phi minus 1 equals 1 over phi, the reciprocal of phi. So phi is a number such that when I add 1 to it, I get its square, and when I subtract 1 to it, 1 from it, I get its reciprocal, which is not exactly a common property of numbers. Now finally, I promised you a solution for what phi is, and that comes by observing that it's the solution to a quadratic equation, and we could solve that by applying the quadratic formula. Minus b plus or minus square root of b squared minus 4ac over 2a, where a, b, and c refer here to the coefficients. A is the 1 coefficient here, b is the minus 1 here, and c is the minus 1 here. So I have another video on the quadratic formula, if you're curious where this came from, but if we take it for granted and apply it, what we get is minus 1 plus or minus the square root of minus 1 squared minus 4 times 1 times negative 1, all divided by 2 times 1, which is equal to 1 plus or minus 1 plus 4, which is 5, divided by 2. And since we're talking about this ratio here, which is clearly positive, we can reject the negative root and get our final answer. The golden ratio is equal to 1 plus the square root of 5 divided by 2.